Thank you. So my research work as a graduate student was based on acoustic emission monitoring of reinforced concrete structures. And but more recently, I've gotten interested in expanding that a little bit and actually looking in what I would call a more active approach, which is also based on ultrasonic waves in the structure. So the title here, passive and active ultrasonic stress wave-based monitoring. Passive refers basically what we would more maybe what is better known as acoustic emission monitoring. And the active part is when we have a known source that generates stress waves. Okay, so the idea is what we're working on. I'm showing sort of the overall goals here of our research. We want to try to come up with methods to combine these two approaches. I will show you why I think there's actually a benefit of not only using a passive approach, so acoustic emission, or an active approach, but actually combine them, because the transducer network that is used is exactly the same. So if we do it right, we can use both of these methods combined, and there's real advantages to that. So that's one of the overall research objectives of what I'm working on. The second one here is explore how maybe machine learning could help in this process of help characterizing signals. And I say here in progress because we are not at the end here, we're only at the beginning here. What we then want to look at next is look at embedded transducer networks. So the research that I will show here still is based part on surface mounted sensors, but I've started using embedded transducers, so ultrasonic sensors that can be completely embedded in the concrete. And that has also quite a few advantages in terms of the coupling that's more consistent, temperature variations, and so on. And a future work, we'll talk about that a little bit later, is actually how we want to improve the machine learning part by also working with both of these methods. So in this presentation today, I'm going to focus on the first two research goals. Okay, so active versus passive approach, I already mentioned it. In the passive approach over here, we call that traditional acoustic emission monitoring. We have a transducer network, so sensors either on the surface or embedded in the concrete that measure basically tiny little surface or vibrations on the surface that are caused by some source that happens internally. So the material is overloaded somewhere, and that basically initiates a stress wave that propagates out. A little earthquake, basically. That's very appealing, so we can capture internal fracture as it occurs. The problem is, initially, we have no clue where the source is. We don't know what the reason is. We don't know anything. We just pick up signals, waveforms at these locations on the transducer network, but we don't know where the source is. So it's spontaneous. We cannot really well control it. And so we can also not repeat it. Once such an energy is released, you can't do it again. It's released. So each acoustic emission is unique. So this is why I call this the passive ultrasonic stress wave monitoring approach. So here's just a little sketch, some beam, an internal source, typical sort of waves radiating from it, one transducer shown for simplicity, and then sort of a typical signal that you would collect. In the active approach, we also have transducers or sensors sitting on the surface, but we're using them. I'm showing only two here, one as a transmitter, the other one as a receiver. And now I just continuously, I send a pulse. And I know the location of where I do that. I know exactly what the signal looks like. And I know where my receiver is. So in this case, the source is exactly known. Its location is known. The shape of the signal that I'm sending is fairly well known. And when I send it is known. So this is controlled and it's really highly repeatable. And if I use, again, embedded sensors, then I have also very high consistency there. So what I can do here is, rather than capturing these active sources, I can actually measure the things that happen in between the active fracture sources. So things that might change really slowly. So it could be ASR, it could be creep, it could be temperature variations, could be other deterioration mechanisms. Maybe you have heard of coda wave interferometry. That's one way to look at the data. It's extremely sensitive. So these are the two approaches, and that's what I've been interested in recently, how we can best combine them, because we have the same transducers sitting there anyway. So to do that, we did. I took advantage of a large-scale test we did in my laboratory with a colleague. So this is a cross-section of a 1950s reinforced concrete bridge in Oregon. This is a bent here with two columns, and you can see a reinforced concrete deck girder bridge. Here, this is reinforced concrete, not pre-stressed. Turns out they have pretty deficient column details down here, not very well detailed for strong earthquakes. Now, where I live in the Pacific Northwest, we expect a mega thrust earthquake to occur in the next 50 years or so. So we better understand how well they will perform. So we did tests in the laboratory. Basically, we built a sub-assembly at around the inflection point here, built this full scale. So this is 24 by 24 inch diameter, about 8 feet tall. And then this footing is 6 by 6 feet and 1.5 foot thick. So it's a big specimen. I instrumented this. I will show on the next slide exactly how we have ultrasonic transducers. The idea being, maybe I could, as some event occur, some earthquake occurs, I could do the monitoring and then characterize how much damage there might be in the column. We used a specially designed reverse cyclic loading protocol to do this that is representative of such a big megathrust earthquake, a subduction zone earthquake. And we also had a special way to actually vary the axial force. So if you know structural dynamics, as this thing starts to move left and right, there's actually a variation in the axial load. So we also try to capture that. Here is a photo of the specimen during testing. This is a little small here, but there's already quite a big crack here. So basically, we're loading it here at the top. So we're starting to push it back and forth to higher and higher displacements. And we also vary the axial load by doing that to really represent what the loading looks like. What I instrumented this column with is, on the one hand, I had three, I call them acoustic emission transducers. They're basically ultrasonic sensors. You can see AE1, AE2, AE3, the blue dots. And they were traditional surface sensors sitting on the backside of the column here. So 1, 2, 3. I also embedded these fairly new ultrasonic transducers that can be directly cast into the concrete, and they're sitting basically in the center of the column. And you can see them here, US1, US2, US2, and I call this UST because that was the one that actually sent the pulses. We call that, those are for the embedded transducers, they were used for the active approach. And I'm basically transmitting a pulse every 1 second. I'm transmitting a 60 kilohertz pulse. And so the wave travels up and down. And I can basically sort of capture information within these two regions here, region 1 and region 2. Interesting, of course, I would expect that there's some differences down here. I would expect the biggest bending moments, so some plastic hinge formation. That's what they look like. And you can see sort of shown here where they are located within the column. Here's the loading protocol. It's a little complicated, but we're basically imposing a displacement, which is the green trace. Down here we have time in seconds, so it's a fairly big number. We tested this over many, many hours, over an entire day. You can see it slowly increases. It's reverse cyclic, so we push and pull and push and pull and go to higher and higher cycles. The black trace is the axial load. So that varies along with the horizontal displacement, again, because of this P delta effect. So as the bend is moving, there's some additional load that's being pushed on the column, because of overturning. You see 1 through these Roman numerals, 1 through 6, that's sort of the damage states that we designated. So 1 is completely linear, uncracked behavior. Then we had some cracking, some initial cracking in phase 2, initial yield here, and then full yield of the reinforcement here. And then we get into like spalling and so on. And then over here, that's where the whole story is over. Down here, these are damage photos of the surface of damage state 2 to 6. So 5 images here. You can see how the cracking basically increases and we have more and more deterioration imposed in the concrete. Here's some sample data that I collected. Top one is from acoustic emission sensor 2. That's basically the one that was sitting here somewhat in the middle of the column. And what I'm showing here is on the x-axis, we have time. On the y-axis, I just have amplitude. So each time an acoustic emission arrives, I calculate the amplitude. And we had a good introduction in the first presentation, what that is. And then I just plot a little dot. So this is, you can see here, there's a lot going on here. We would have to actually zoom in a little bit to see. But each time I'm imposing new cracking, that's pretty much when I can see a nice little tree of acoustic emission hits basically arriving. The orange line is cumulative number of hits, so just adding up how many signals I collect. This down here is the ultrasonic wave field. So what this really is, remember, I'm sending a signal every second from the middle transducer, and this is for the region 1. So I'm showing the signals that are recorded at the bottom here, at this transducer. So I'm sending up there, and here I'm receiving. So I'm recording these waveforms, and then I'm stacking them in the vertical direction and just create a surface plot. So that's what this really is. It's almost equivalent to a B-scan if you know what that is in non-destructive testing. So if I took a slice here and plotted it, it would look like a regular transient signal that you would see that would look similar to an acoustic emission. I'll show an example on the next slide. So if I line them up, I get sort of this bird's eye view of all the signals collected stacked horizontally. And it's quite interesting what you see. For example, up here where it's we have these like horizontal lines. So this is just noise. This bluish band is just noise, but then here I can see the P wave arrival. So that's when that first wave arrives at the sensor. As I move to more and more displacement, you can see that that sort of starts to be disrupted a little bit. So there's some changes there, and that makes sense. Once I have cracks in there, the wave has to travel just a little bit longer so that that band shifts down. And so when I look here, you can see that here, for example, very well. So there's a band and then it drops a little bit, and the amplitude also sort of gets lost a little bit. So there's more damping because the column is being pushed, the cracks are open. And then so on. So this lines up directly with the sort of displacement history of the horizontal displacement imposed in the column. You can see these two sort of blue bands. That's when we accidentally, turns out that was actually a nice thing to happen, accidentally unloaded the column. So we had some issue with the hydraulic system and the column unloaded, and we could clearly see what effect that had here. So it's interesting to actually observe that. The other thing we can see, there's quite a bit of structure here as we move from here. There's sort of this almost triangular shaped structure here. So as I move to more and more cracking and damage in the column, those bright colors go away, and I only have them in the beginning, and back here it turns more blue and blue, meaning there's just more attenuation in the signals. So looking at this, we thought this it's changing, but it's sort of gradually changing. There might be a good way to use machine learning to sort of analyze this wealth of data. You could represent the same thing with acoustic emission, but it would look pretty chaotic because the signals do not gradually change the way they do with the ultrasonic waves, because here we control the source, remember. Here the sources are random. Oh, do this. Okay, here are some examples. Acoustic emission signals, just 2 examples collected. Amplitude versus time. You can see that these are just 2 I collected, and you can see the amplitude varies quite a bit, right? This has an amplitude of 8 volts. This one has an amplitude of 0.11 volts. So the signals just differ quite a bit for this. Down here, I have an example of an ultrasonic signal. So where this is the source, actually, it's very well controlled. It's this pulse that I send every second. That's the frequency spectrum of the pulse. And that's an example of a received signal. So here again, this is basically the signals that I all stack horizontally, right? That you saw on the previous image. And if I look at the frequency spectrum and do a little bit of moving average, you can see that basically represents the same frequency spectrum. Up here, the frequency is sort of within a certain band, but it's a little bit more random. Okay, so what to do with this data? There's a lot of things we can do just with the acoustic emission data. That a lot of people have looked at that. There's p-value analysis. There's all kinds of things that can be done. Clustering, we've heard that today too. But what we wanted to focus on first is on the ultrasonic data. So on the active approach, because we see this structure sort of gradually change. So the first thing we looked at is simply calculating the correlation coefficient between two signals. So I'm showing two signals here. And basically you could think of it, one is a reference signal and the other one is a signal collected at time t. And you simply calculate the correlation coefficient that gives you a value between 0 and 1, right? And this is basically just thinking of it that this is a very low dimension, that the signals have very low dimensional, just a one-dimensional structure. So it's a very simple way of comparing two signals. It works pretty well. It's actually pretty sensitive to capture changes between one and the next signal, but it's probably too simple to capture the potentially complex changes that the signals undergo by these deterioration over time. Here is just another way of showing this one-dimensional nature of that space and how we can calculate or think of the correlation coefficient as an angle between these two spaces or these two lines. So if the angle is 0, then the two completely align. It means that the signals are the same. If that angle starts to open up, if they're 90 degrees, it means the correlation coefficient is 0. They are basically very different. So the machine learning approach, and I should have acknowledged, to be fair, my colleague who is doing this part, I wish he would be here to present this, John Lepore. He is actively doing research on machine learning, so that's what we're working on together. But one thing we thought we could look at is this subspace clustering. That's sort of one thing that he has been working on for a while. And what we do here, rather than having just a very simple low or just two simple subspaces, we can have K or a high number of subspaces or subspaces. And basically what we want to do is we want to try to group or cluster the different waveforms that belong together and associate them with these subspaces. And so that's sort of the hypothesis. So if we can take these signals or waveforms on the different conditions, and by condition I mean different stages of damage, maybe they would sort of cluster in these different spaces. So the goal is to basically separate these signals without prior knowledge. So this is actually what we call an unsupervised learning algorithm, and see if they coincide with different stages of damage. So can we predict how badly damaged the column is? This algorithm, I should say, has applications from image processing, computer vision. You can see that here, motion segmentation, gesture classification. So we have to be careful that we have to keep in mind that we might have to adapt this algorithm a little bit. We're not quite doing the same thing. So a very simple approach. So we know we want to try to cluster these in different subspaces. And then what comes in, we need some sort of an algorithm that solves an optimization problem, right? There's always among all these machine learning algorithms, at some point, there's an optimization problem to be solved. So this K-subspaces algorithm does that. It's pretty well known. You see, it basically starts with some random number of subspaces, clusters points, there's a principal component analysis involved, and then it repeats the process until there's some convergence, there's a cost function involved, so until you have convergence. This works well for image processing, so for doing that on images. And it has a good performance when it's initialized well, because you have to, again, start at some initial point here. It's pretty computationally efficient, the way complexity scales linearly with number of data points or waveforms in our case. The problem is here initialization might be a problem. And one thing is that is different for our data. We have this sort of sequential nature, this evolution of the signals from good condition to bad condition that we're not considering. That's actually information that we need to somehow incorporate into this process. Here's just an example of a more complicated subspace structure. So where we have two simple two one-dimensional subspaces and a two-dimensional subspace. So what he came up with, what he's been working on, is this sequential K-subspace modeling. And here I'm showing the loading protocol again. The red lines are actually what we call condition changes. And it's a little bit more than the damage states that we showed. We also drew a red line anytime the displacement was increased. That's why we have so many different red lines here. But anytime we believe there's something changes in the condition of the column, we basically denoted that with a red line. And so the idea here is now that this sequential K-subspace modeling algorithm would account for the fact that we have this evolution, this change. So it would initialize according to basically going from left to right, from little damage to more damage. It also encourages that these that signals that lie next to each other should belong to the same subspace. The other one does that not. So this is already a little bit modified to account for the nature here of our signals. And so here we basically, what I'm presenting today is just some preliminary data or some preliminary results. The red lines are what we observed, and the black dashed lines are the ones that were predicted by our initial sequential K-subspace model. So the idea here is that the first line would coincide with the change, and would basically, it would say now a new cluster of events, a cluster of signals should start. So you can see that there's many more black ones compared to the red ones. So we're definitely not there yet. We compared it actually with some other state-of-the-art algorithms. We have isolation forest. I think that's an anomaly detection algorithm. Cosine distance is basically just simple correlation between signals. This is another algorithm that I don't know. Sequential KSS is what we proposed. And then you have these two performance measure, precision and recall, that are related to how well you predict the actual observed events that you want. And then F1 is just the harmonic mean between the two. So without doing too much tweaking, just trying a little bit with this algorithm, we could definitely see that this sequential KSS algorithm significantly has a significantly better precision and recall compared to the other algorithms. Here we're only looking at events, meaning we're looking only at the red lines that actually indicate the damage states. And over here, we're also including the loading changes. So this one would basically relate just to the 6 damage states. And this one would include all the red lines here. Okay, so just to summarize it, I introduced this idea of active and passive ultrasonic monitoring. Here we showed it on a large scale experiment where we wanted to see if we can if we could cluster the signals that we get and that they line up with the evolution of damage that we see in the column. Again, the idea would be if an earthquake happens and you have this network embedded, you might be able to tell something about the condition. If the member is not accessible, that might be a really nice thing to have. We looked at some different algorithms from very simple to this sequential K-subspaces, which is work in progress. And we showed that this initial setup really outperformed the other algorithms. So the next step will be, because we haven't used the acoustic emission data at all. But as I said, with acoustic emission, we can capture active fracture processes. So the idea that we have, that we use that information, so when these little pops happen, that would inform the algorithm and say, hey, something just happened. You might want to check if this means there might be a new cluster, a new subspace. So that's the idea that we sort of roughly have what our next steps will be. So here, I'm just zooming in on the very beginning here. You can see I'm not showing the loading here, but at this point here, we basically, that's the first time we introduced cracking in the column, at least cracking that we were able to observe, I should say, right? That's always the problem. Acoustic emission is also pretty sensitive, so you might miss the first ones. But each time you have a little cluster of acoustic emission hits, some internal fracture occurred that you picked up. That's where we're at, and that's all I have. Thank you.
Professor, I have a question.
Yeah.
So did you try comparing the predictions from your model to simple UPV measurements? As in, so taking a UPV measurement is very simple, right? Just going onto the field, put a transmitter receiver and collect UPV data. So can you predict, like, for example, you mentioned locations where there were events, right? Like your red lines. Can you predict those by simple UPV measurements? Like, do you see a considerable reduction in UPV? Because your eventual goal is to try predicting the state of the structure, right? How, I mean, can you just simply do it using UPV, or the model in this case performs better? It's more sensitive to smaller changes in the structure. Like, I'm not sure if I conveyed my question.
I think UPV, you mean ultrasonic pulse velocity.
Pulse velocity, right?
Yeah.
Pulse velocity.
Yeah, we can see that. So if you think back of that plot where I lined up the ultrasonic signals, you can see in the very beginning when there's no damage.
I mean, I cannot see you. I'm online.
Yes. So early on, when you have sort of linear behavior and there's just a little bit of push-pull on the column, that doesn't affect the ultrasonic pulse velocity. It really doesn't.
Okay.
But if you look later down in the signal, so what we would call down here the coda portion, you could still see something, right?
Okay.
But once you have initial cracking, once you have, usually at the very bottom forms a crack. And once that has formed, then you can definitely see it.
Okay.
So that's another indicator. Yeah. I mean, that's right.
Yeah. I mean, so that was my question. Like, does a very simple indicator like the pulse velocity, how does it perform to a more complicated way of trying to identify the damage state? So
yeah.
Okay.
No, absolutely, you're right. No, you can see it there too. Yep.
Thanks for clarifying.
Thank you. So I have a quick question. It's more on application. So for this one, you have the ultrasonic sensors embedded, right? Can you do this with surface ones, or will you need to embed them? Like if
no.
For an existing condition?
Yeah, no, you can. So first of all, I've done some field work where we embedded these in the structure too. If the owner will let you do it, you drill in, you push the transducer in, and you put a special slightly expansive grout in. That will really, create a good bonding. That works well. We did that on a historic structure and collected months worth of data. That is absolutely possible. But it doesn't matter. You can do it with surface mounted sensors as well. There, the problem I have found is coupling. Depending on what you do, especially for the coda portion, really small changes in the coupling have just throw everything off. So if you just have humidity changes, or if you use a bonding agent that dries up, it will affect everything. So the sensor the embeddable sensor is about 75 millimeters long and has a diameter of 20 millimeters. Well, it depends if you're already monitoring in some way. I mean, usually you install the system and then you start monitoring, right? So that the installation process does not interfere with your data collection. Now, if you have an existing network and you're already monitoring and then you install extra sensors, then you will definitely see that. The data, the signals will probably look a little bit different, right? If I take a column where I put them in, when I cast them in, and I do the same column where I drill them in, and I compare the data, it will look a little bit different. But that actually doesn't matter. Because what I'm looking for is relative changes between the signals. So I'm not looking for an absolute, that the wave should look, or the waveform should have a specific absolute shape. I don't care about that. I care about consistency between measurements And so if that signal looks a little bit different compared to another setup, doesn't matter. I'm looking for changes between signals. That's another advantage of this. Yeah.
So with those, do you also have time of arrival of the signal, right? Can you do imaging while things are happening? Like, can you try to kind of generate an image of the internal status of the column?
If you have enough sensors, you could, I think. Yeah. I mean, I deliberately like to use as few sensors as possible to keep it practical, right? I don't want to, and actually, the way I showed those ultrasonic regions rather than just a line, because what we have seen is with coda waves, when you look later in the signal portion, you can really capture stuff that's in a region, not just in the direct path. When you do UPV, ultrasonic pulse velocity, then you sort of assume a fairly straight path, and then you don't see much. But if you consider the later portions of the signal, the way I sort of visualized it on that image, you actually collect information from quite a big region. We did some measurements where we drilled little holes far away from the direct path, and we could sense them, no problem. So in some way, it's not imaging, but it's definitely capturing a volume, not just a line. And if you wanted to image, you could do it, but you would have to have many more sensors, right? And then you would have to you could do something like tomography almost too. Yeah. But the point here is to keep it simple and to hopefully get enough information to sort of characterize the state of damage after an event. So that's why we use as few sensors as possible. And you can space them out much more than we did. Some people there's infield tests where they have spaced them out 5 meters from each other. So I don't want to take more.
So let's thank our speaker one more time.
Thank you.